So in this example, we've been asked to find out whether this little particle is in equilibrium. So we've got a bunch of forces. So we've got 4 forces in total, all of them acting on this little particle. Now later, when we're doing some more practical problems, what we'll find is we can define the particle to be the point at which all these vectors, so all our force vectors, converge. At the moment, we're dealing with a kind of theoretical construct where we've got this imaginary particle and got forces acting on it. And we'll see when we get to some more complicated examples that what we can do is we can choose a particle in our system, and the way we choose it is by the fact that all of the vectors converge onto the point at which that particle exists. Okay, so that's for a bit later, but this first one we're trying to figure out whether or not this particle's in static equilibrium. So we're using Newton's first law. In our case, we're looking at things at rest. We're not worried at the moment about things moving at constant velocity. And Newton's first law says that if no force acts on an object, then it'll remain at rest. And so if the net force of all these forces, so when we combine all these forces, we'll get a resultant. If the magnitude of that is 0, then the particle is at rest and we're at static equilibrium. So as before, this is very similar to combining vectors to get your resultant vector. Just when we're finished combining them all, we should come out with an answer of 0. So there's 2 ways we combine vectors. One was to use just graphical method. So we can put them all nose to tail, or in the case of forces, sometimes we just imagine putting them nose to tail. Or we can figure out the x and y components, add up all the x components, add up all the y components, and figure out if we've got 0 for the x and y components. So let's start with the graphical first. Again, I'll just fast forward through the parts that are a little bit time consuming, but we'll start with the graphical method first. So what I might do is I'll just move the original sketch across to the side. And one thing just to be careful of, I'm just going to copy this because I know that I've drawn it to scale already. So I'm going to use it directly. But if you're doing a problem from a book, just be careful about assuming that in the problem the vectors have been drawn to scale. So sometimes when you're doing an engineering problem, you don't have time to sit and draw the full scale drawing, although at your stage I recommend you do a scale drawing, or at least as close as possible to scale. But when you're doing quick sketches, more generally, as you become more practiced using this, the different methodologies, you might not draw it to scale, and the same is true of textbooks. They may not draw the vectors to scale in the textbook. So just when you redraw it, be careful that you redraw it to scale. In this case, the scale I've used is 10 divisions is 100 newtons. So 1 division is 10 newtons. So you'll see this is 100, 200, 300 newtons long. Okay, so what I'll do is I'll just quickly look at, work through this and join them all nose to tail, and we'll see what we get, whether this particle is in equilibrium or not. So I'll see you on the other side of the fast forward. So I've now joined all those nose to tail. So you remember before we were saying when we're doing the sketch, we wouldn't necessarily want to draw them this way because it looks like the point of application of the vector has changed. But in this case, I'm just going to draw them nose to tail like that. What you'll see is we're almost getting a closed path. So it looks like this particle will be in static equilibrium, but to be sure, we'd want to do this more accurately. So therefore, we want to do the method we used previously, where we're finding all the x and y components of these vectors. Now at this stage, we're getting to the point where we should be getting pretty good at using SOHCAHTOA and your Pythagoras. So I'm not going to write it all out. What I might do is make up a bit of a table, and I'll do all my calculations into that table, and we'll see what results we get. So again, I'll just fast forward this so that you're not sitting through me doing all the calculations, but let me work through that and I'll get you on the other side. I'll just pause here for a minute. So I've worked through and I've looked at what the x and y components are. There's a bit of a shortcut here. F1's already in the x direction, so we can just jump straight to F1x is equal to that. Similarly, F2 was in the y direction, so we can just jump straight to this value, this magnitude is equal to F2y, because it's already in the right direction. For the other two, I've just marked out my x and y components, and I'm thinking about directions at the moment. So this is going to be, now let's just check if the original problem gave us an x and y direction. No, it didn't, so we'd better just write that as well. And so we're just going to mark on what we're assuming for x and y. We'll have a quick think about it before we start, if there's any advantage to changing it from the usual direction of x to the right and y vertically upwards. In this case, I can't see any particular advantage in one way or the other. So like, for example, maybe putting y downwards or putting x towards the left. In this case, just the standard directions for x and y will do the job as well as any other direction. One thing we could have done, if these weren't, sometimes you can line these up so that you get this effect. So you line them up with one or two of the vectors so that you can jump straight to the vector as its own component. So it's only got an x component or it's only got a y component. If you can find a direction, so for example, if we had a problem like this, just quickly draw it in green. So if we had a problem like this, where we had one vector like this, one vector like that, and another vector down here, say, then it would make our calcs a lot quicker. I'll try and draw that so it's as close as possible. If we made the x and y direction like so, so that this was in the same direction as this vector, this was in the same direction as that vector, therefore this would only have an x component. So this vector here would only have an x component, this would only have a y component, so we'd only have to use sine, cos, and tan for one of the vectors, this one down here. Whereas if we use the usual x and y directions, we would need to calculate x and y components for all of those vectors. So it is worth pausing to have a think about what direction you take your x and y directions in when you're doing these types of problems. Okay, so what was I saying? Yeah, so we're thinking about our x and y directions, whether they're positive or negative. So this is going to be positive. This one here is going to be negative. This is going to have negative x and negative y components. This one here will have a negative x component, but it'll have a positive y component. So what I'll do next is I'll just look for I'll work out what all my x components are and add them together. And then I'll work out all my y components and add those together, and we'll see what result we get. Okay, so we worked through those calculations. So I've found all my x components, added them together. I've got 0 newtons, so I've got 0 component of force in the x direction. Then I've determined all the y components, been careful with the directions, added all those together, and I've got 0 component for the y direction as well. So therefore, this particle is in static equilibrium because both the x and y component are 0. Okay, so therefore we know that particle, so the question was asking, is the particle in static equilibrium? Particle is in static equilibrium. Okay, so quick summary. So we've got two ways we can decide whether a particle is in static equilibrium. One of them is to do it graphically, and so you just take all those vectors, join them nose to tail, And if they come back to the start point, then you've got static equilibrium. So you remember when we're just looking at forces, I'll just do this roughly. So when we're looking at forces, we had different components of force, and we wanted to find the resultant, then we would just take those components and place them nose to tail. It's going to be a bit messy, this one, but that's okay. This one's going to join nose to tail here, and your resultant is just the vector which joins the starting point to the end point. So resultant vector is here. You know you've got static equilibrium if the path of all these vectors comes back to where it started, so therefore you've got a resultant of 0. So in this case we followed nose to tail for all the vectors, and it's ended up back at the start point, approximately, a little bit inaccurate due to my drawing, probably because this is not flat. And so because we're coming back to the start point, then we've got static equilibrium. Alternatively, the other rule is that if you determine all your x and y components and you add up your x components, you get 0, add up your y components, you get 0, then that's also static equilibrium. Just a quick note, this little symbol here, the sigma fx, so this is capital sigma, a Greek letter. Sigma fx just means add up all the x components. Similarly, sigma fy just means add up all your y components. We've got two rules for determining if something's in static equilibrium. Graphically, let me just write this. Static equilibrium if and only if closed vector path or the other rule is you've got static equilibrium if and only if the sum of your x components is equal to 0 and the sum of your y components is equal to 0. Okay, so this little double-headed arrow, that means if and only if. Another way you'll read this in the textbooks is they'll say this is a necessary and sufficient condition. So all it means is if you've got static equilibrium, you'll have to have a closed vector path. But similarly, if you have a closed vector path, you must have static equilibrium. Or if you've got static equilibrium, the sum of your x and y components will be 0. Alternatively, if the sum of your x and y components are 0, then you'll have static equilibrium. Okay, so that's looked at static equilibrium. Let's have a look at how we can use static equilibrium to find some forces.